Hello YouTube viewers, welcome to my channel Science Technology. In today's show, Rocket Monday, we're gonna talk about Firefly, Aerospace, Blue Ghost, mission number 1. So let's dive deep into it. So this puppy, Blue Ghost, is a platform, so to say. It's a class of lunar lander. Basically, how Falcon 9 is an orbital class rocket, this puppy is a lunar lander. And it's made by Firefly Aerospace during, not during would be right word, under the tutelage of CLPS, Commercial Lunar Payload Service. Now, basically, because of the success of SpaceX, NASA realized that it is a really good idea to invest into commercial option. Now, what does that mean? That simply means NASA is going to front load the contract and they're going to bear the risk and all the penalty that comes with it. They're going to bear that. Now, do they get at the end of it? Well, options, lot of options, because here's it. Without SpaceX, there is nothing. Like there is nothing. Now, options matters because again, technically everybody was like, oh, why do you are investing money in SpaceX? You have Boeing who's going to build your next generation craft. We all know how that went. So NASA learned the lesson very hard way. And again, Space Shuttle also taught them very important lesson. Thou shall not have single point failure. So CLISP is basically layover of that mission. Basically, that was built, the first commercial resupply mission was built for ISS resupplying. That worked flawlessly. This is similar thing built for specifically lunar payload. So the idea is they're gonna try to innovate with multiple options, multiple provider, and if they try with 12 players, at least 2 or 3 of them should get the job done. So that's the idea. So what does this platform provide you as the customer, so to say? Now be mindful, commercial lunar payload service simply means you get the call the first tip. Basically NASA is like, bro, I'm the first in the line. But once that NASA's contract, NASA is like, let's say 3 launches per year. What after that? You can do as many as you want. So that's the only requirement of CLISP. So basically you cannot like, okay, let's sideline NASA and let's launch some private. No, NASA must be fulfilled first. That's the part of the contract. And after that, you can go YOLO. And that's the intent of it. Basically, NASA front load the cost and they get the first steps and they have tools. Because again, if NASA tried to do it the old way, they're going to be bankrupt. So that's why they are trying this. So this platform will give you data, power, thermal systems, and envelope. The envelope is around 650 watts of electrical power and 150 kilograms of mass. So you have to work inside that envelope. What you can fit into that, that's up to you. If you could have like one giant observatory at that kind of power envelope, you could have like multiple small instruments, whatever have you. That's the envelope, that's the platform limitation, and that's what you do. Because you have to understand, whenever somebody is going to the moon to do experiment, going to the moon is the most expensive part, even though they do not want to worry about that. Basically, hey, I want to build a drill that can drill onto moon. You want to spend time on that. You do not want to spend, okay, how the heck we're gonna cool it? You want somebody else to take care of that. You do not want to like, okay, I'm building this X-ray imager that's gonna work on moon and we're gonna see all those cool things. You do not want to figure out how the heck I'm gonna cool the damn thing, how the heck I'm gonna transport the damn thing, how the heck I'm gonna, basically have a communication bandwidth, all of that. You do not want to worry about that. So this is what they are doing. Basically, it's like, hey, your payload, I got this. That's it. So they have vertical integration component. This is another quality control point of view, because the more things that are vertically integrated, the tighter the tolerance you're going to get, the tighter quality control you're going to have. And what does that mean? That simply means your oops rate goes down. Meaning if they launch 10, the likelihood of 8 being successful is very high. If this was not vertically integrated, you can have the same scenario that Boeing did. It's like, no, we designed it perfectly, but the booster, the small rocket that was provided by some of the thrusters, that was not up to the spec. That is removed. So it does make it a bit expensive, does require a bit more front loading in cash, but does have the benefit that quality control becomes better. And any failure is your own failure, so you improve exponentially rather than pointing blame. So that's why this is a very good peace of mind, so to say. And the longer they use this, the better it becomes. That's why SpaceX is so goddamn good. And then you have to understand that they also provide extensive qualification testing. Because if you really think about it, like if you really look into the things, it's like how hard it is to make things for moon. That's child's play. It's the qualification that's going to bankrupt you. So basically, that's what they provide. So this is Blue Ghost, and this is the truck that they are using for transporting it. Basically transporting from their ISO 8 factory to SpaceX. So this puppy, the whole system was put in motion on 4 February 2021. NASA awarded Firefly a contract. Again, the idea is there's supposed to be multiple contract like this. So Firefly contract of around 93.3 million. Now, if you know NASA, 93 million is like chump change. It's like it's a rounding error for them. To give you a context, SLS launch is costing more than 2 billion. Yeah, with a big B per launch. So 93 million for lunar mission, it's take it and go. I don't have time to worry about it. So that's the whole point. And what did they ask for it in return? The idea was 10 science investigation and tech demonstration. You have to understand this core aspect. If you're like, okay, I'm going to build this computer that's going to work in lunar environment, how the heck do you know? Now, again, you have to understand, in 1969 era, everything was like do or die. So risk taking was like just go, either it works or it does not work, just go, do your best and go. That is no longer acceptable, specifically because we want to stay in the moon. That's the whole that's the core and point of Artemis. Stay on the goddamn moon, not just like, okay, go and come back without dying. It's like go and stay. That's the whole point. Go and stay for longer and longer duration, and hopefully before the next series of missions are done, you have a permanent presence on moon, exactly how we have permanent presence in space using ISS. So for that reason, you need a lot of tech demonstration. It's like, we think this material of basically fabric that we are utilizing for outer layer of spacesuit can last in lunar surface. How do you know? You can do all the testing, but you can't replicate every nuance detail, so to say, and harshness and low gravity. You cannot simulate that on Earth. So tada, put it on moon. So, and that's what NASA calls technological readiness level. It is utilized worldwide. So technological level 8 is what you want, but here's the deal, how the heck you get to it? 1, 2, 3, 4, it can be done on lab, but 3, 4, 5, 6, you have to do small testing missions. That's what NASA is focusing on. Why? Because it's a risky mission. They can put this 93 million, but here's the, they have no chance of knowing whether it's going to be successful or not. It's not a James Webb Space Telescope where they're risking all the money. To give you a context of it, that puppy was $10 billion. So yeah, that's a high risk mission. This is like a low risk. So they are utilizing for technology demonstration. Basically, we think this could work. Let's test it, because there is no substitute of real world testing. So doing that. And the original target was Moon 2023. It got delayed a bit, not too much. And Firefly Alpha rocket, because again, most company know Firefly is a rocket company. They did had Alpha rocket, but that rocket was too underpowered for this sort of mission. So they had to switch to powerful rockets. Falcon 9, and Falcon 9 launched this puppy on 15 January 2025 at 6:11 morning Universal Time Coordinate. And here's the thing, Falcon 9 is a low Earth orbit vehicle. So how the heck you go to moon? Well, here's the deal. If you do not have time sensitive equipment, aka human, you can take your time, you can take your sweet time, and you can do what we call orbit raising maneuvers. Basically, you go into enough oomph, enough delta V in low Earth orbit, and then you have thrusters. That thrusters goes pew, pew, pew. That's how you do. You keep orbit raising it, and it takes time. That's the penalty. Instead of going to the moon in 3 days, it could take upwards of 15 days or maybe even longer. So that's the penalty. Benefit, you can use a very small rocket to go to the moon without too much issue. But that does mean all of your equipment has to go through radiation for much longer. So you have to deal with that. So now Falcon 9 is overbuilt for that mission. So they are like, okay, what if we put another lunar mission, Hakato R mission 2, that is a second lunar lander that they are putting on that in this exact rocket, and it's gonna reach their different time. Why? Because their orbit raising maneuver calculations are a bit different. So tada, that's why a low Earth orbit rocket can yeet things to moon. Orbit raising is awesome if you have time. If you do not have time, that's not a good thing. But if you have time, you can easily launch even on PSLV, like India's small satellite launch vehicle, polar satellite launch vehicle. We can launch some pretty heavy stuff to moon or even to Mars. So this is the launch. Now, what about landing? Now, landing was boring, meaning it was awesome. Now, it all went according to planned trajectory. That's why it was boring. That's why it's awesome. It's supposed to be like that. Like, you know, you do not want your plane landing to be exciting or things like that. You just want it to be boring. Like, I was sleeping and I woke up, a plane was like, you know, deboarding. That's what you want. So it was everything going exactly how it went, supposed to went. However, let that be very clear, there were certain minor hiccups. One hiccup was that it has a fit, like a very bowl shape kind of feet, and that feet has a brake wire. It's exact same technology that was used in Apollo era. Basically, they also had that issue. They did not have LiDAR and all that, and again, they wanted something foolproof, so they also had prongs, so to say. Prongs, once they break, they're like, no, okay, we have touched the lunar surface. So it had the same thing. Now, the bowl was like this, and they're supposed to go like this, so breaking the wire. But one bowl landed on some sort of rock or some sort of missile. It did not break the wire. It did land it. It's like completely solid, planted, landed, but it did not break the wire fire. So that's why in the live stream you will see 3 symbols turning green, 1 not turning, but does not mean it's like floating or like it's standing like a tripod. No, it's done, it's sorted. It's just that sensor did not trip. And be mindful, it has multiple sensors to make sure that it knows what's happening, and all sensors are like we good, only that sensor is not good. And after that, you also have to understand during the this whole mission, specifically the touchdown mission, the computer switched to a finer units. Basically, instead of meters, it went into millimeters, and that's why when you are watching the live stream, the number goes from 1 meter to 800, and the millimeter was not. The graphics designer did not port that properly, so it did not show 800 millimeter. It's just like 800. So you're like, okay, how the heck it went from 1 to 800? So that was there. But again, everything was as it should be. Non-exciting, simple, boring. That's how it should be. And this is a footage we just got very quickly, where you can see the high gain antenna aiming towards Earth. So this is the landing part. Basically as it should be, because last year was not kind. Now, what about the payloads? Again, NASA asked for more than enough payload. So it has lunar instrumentation for subsurface thermal exploration with rapidity. Yeah, it's just a drill with user's compressed air rather than, because again, low gravity, you do not have enough oomph where you can like dun 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 dun. You can't do that. It's a similar kind of variant that one drill that we utilize on Mars, where it's like going tung 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 tung. It's using spring power there. It did not work that well. Here, instead of using spring power, they are utilizing compressed air. So it's a hollow pipe that goes there and it liquefies the lunar surface, and mild gravity plus a little bit of screw motion that should allow them to drill. So again, it will be tested. Lunar planetary vacuum, and you'll be like, how the heck you can do planetary vacuum on a celestial body that does not have vacuum? Well, it's supposed to be vacuum. It's not vacuum. And the idea is you go fachang on the material and you scoop up a little bit, but you do not pull the material up. And it has nozzles that's gonna inject gas into there, causing turbulence. And then you have secondary gas ports, that's going to fire gas through a Venturi effect, so to say. So it's supposed to suck up material. The idea is doing this way should allow you to have less wear and tear. So once you do lunar mining for building habitats and all that, doing scooping like that might look super easy. It is, but it has too much wear and tear component. So utilizing gases could be a much better thing. Like, wouldn't that means we have to carry gases? Nah. If you have any sort of energy source, well, you boil the lunar regolith, more than enough gases. That's not an issue. So that's why they are testing this methodology. So that is planet vacuum. Next generation lunar retroreflectors. So this were NGLR, and this is for people who left their brain in the toilet. It's like, how the heck people know that Apollo mission was true? Well, you have to understand, in Apollo mission they carried basically ancient variant of that made in 1969 lunar reflectors, and they put it everywhere. Now, like, can we know the distance from Earth to Moon using radio waves? Yes and no. Yes, we can utilize radio waves, but you have to use very long radio waves. Only then it can go there, bounce back, come back, and we're gonna know. But again, the wavelength will be so long, it's not gonna be very precise. It's gonna be more than precise enough for, okay, it's 1 light second, quote unquote, more than precise enough for that. But it's not gonna be like this many meters. It's not good enough for meters. You need something with very small wavelength. Radio waves does come to millimeter wavelength. Problem is that atmosphere eats it up. So you need something that has that sort of resolution but can go through the atmosphere. Lasers can do that. Retroreflector allows you to utilize the lasers to test this, and America went there, put retroreflector, gave the coordinates to every Tom, Dick and Harry, including Soviet Union. Everybody tested it. It's a common thing to do in any college and university dealing with astrophysics. It's like a basic stuff. It's like so basic, even Big Bang Theory showed like, it's a thing that people do. It's a common basic thing that people do. And that's why I said, like, if people are, oh, how do we know? It's like, we've been there, tested it, and this is a Mark II variant of that, and this is supposed to allow to know the position of this puppy, at least in the precision of millimeters. Like, you are there, and let that sink in. We are measuring something that is light second away, and resolution is freaking millimeters. It's almost creepy. Like, basically, imagine if you have 500-600 of these on the lunar surface, we can see how it's squishing and all other motions going through it. Basically, tectonic motion. It does have some tectonic lunar quakes, so to say. And again, when it gets bombarded, it does have some shakes. We should be able to detect them. So that's the next generation variant of that. And we have regular adhesion characterization, RAC, this puppy. Now, you have to understand, lunar Apollo Mira just go take your best guess. We cannot do that anymore. So we like, how do we know this material will last well? Create a sample of it, put it in this disk, put it on lunar surface. That's the next best thing we can do. So this is, they are doing it. So they have a lot of sample materials, glass, different type of coatings, different type of fabrics, everything they could figure out, they could put it in there, and they're like, okay, we're gonna test it, expose it to actual lunar surface, and we're gonna figure it out, how does it last. So that's there. And then you have my personal favorite, RAD-PC. So the idea is that whenever we launch stuff in space, back in the days it was not an issue, because again, our gates, the actual MOSFETs and gates that are going on into your computer, those were huge. Like we are talking about 400 nanometer, they were huge. So cosmic ray particles were not able to bit flip them quite easily. But nowadays, our computer chips that we have on surface, they are so tiny, even basically some gamma rays, some not gamma rays, high energy particles that penetrate through the atmosphere, they can bit flip now, because it's so tiny, so sensitive. And the moment you take it outside of Van Allen radiation belt, it's gonna go, it does that. So penalty is that even though you are launching a mission in 2020, your computer hardware literally is from 90s. That giant gate and all that, half of the Mars rovers are like 200 nanometers. So that creates a penalty. We have so much computation power, so cheap computation power, we just can't utilize it. So somebody came up with the idea. It's like, okay, that puppy is slow and super expensive. This is hyper cheap, like cheap as chips, and actually as cheap as chips. What if we had a lot of them and created a software that can handle that penalty? Basically like how we have error correcting code, just a turbocharged variant of that, where we can utilize normal basic bitch computer and be like, okay, we got this. Just put 5 of them and just like run coding fast enough, which be mindful, compared to hardware that is used in deep space, aka anything above a low Earth orbit, basically outside of Van Allen radiation belt, those are slow. And having something that is like, even like, Core2 Duo kind of thing would be like, whoa. Anything modern would be like, damn. So what if we had a lot of them, damn fast equipment, and created a hardware ecosystem and software ecology that can handle that errors, bit flips, random bit flips. It can like, I crashed, no problem. Voodoo. I crashed, voodoo. They keep pushing through, brute force it. So that is RAD-PC. I like that idea. Like, and if it works, it's gonna have magnificent impact on the space development technology. Like magnificent. Basically, like, we can actually do this. Like, and again, that's why they have FPGA boards and all that, so they can design a hardware on the go, so to say. And then they have electrodynamic dust shield, which I want badly. This puppy. So problem is dust. How the heck you take care of it? So they had old technology that they tested is piezoelectric. Basically how my DSLR has a sort of vibrator, which is like a lens sensor cleaning, which never works. But like most cameras have that, it's going to vibrate and remove some dust. It does not work. So somebody came up with the idea, what if we create an electrostatic force field around it? And that force is basically goes like a wave, basically like, magnetic field, so to say. And that wave travels from a center point to outwards, meaning it's like a wave. And dust is acting like a surfer riding on the wave. Small dust can easily be moved by like that, and that's what they're testing. So idea is you have this on a radiator, solar panel, and camera lens. And yes, they have a one that has transparent electrodes. And the idea is dust can sit on it and is like, nope, it just basically walks it off the surface. And again, they have the photos of that. So that's what they're aiming. I hope this works out. I want it in my next generation sensors. It's a holy damn, like sensor dust is such a big issue. If we had this working, awesome. So that is electrodynamic dust shield. That's what we want. Lunar environmental heroispheric X-ray imager is just an X-ray telescope. Lunar metallurgic sound, LMS. And then we have lunar GNS receiver experiment. That's personal favorite. Now you have to understand there is no GPS network on moon. So how the heck you know where you are? You don't. You just hope for the best. Now, was somebody realized our receivers are sensitive enough that they can pick up a lot of secondary chatter that is happening from all the GPS satellite, and we have more than one GPS unit, meaning global positioning network system. We have GPS, we have GLONASS, we have Bindu, we have Galileo, and we have Navik, and Japan also has one. I'm forgetting the name, but you get the point. Like we have more than enough satellites that are radiating. What if we can just calibrate data based on that? And it should work. That's what they're testing it. If it works, awesome. And they have a stereo camera for lunar plume surface studies. Basically, when the rocket goes on its ass, what the heck happens? So the camera for that. And again, The camera worked, everything is there. It's just that bandwidth is limited. That's why we are not seeing the 4K video of it. So core focus is testing next generation technology. That's the whole things are. Other than X-ray, I have no idea what it would be helpful in next generation. But they were like, okay, we have space, we have capacity, just put it there. But everything else is very core focused on. It's like, okay, how can we do a material? How can we know precise range finding? How can we do dust mitigation? How can we test the materials? All of those are very specific things. And I have no idea what's the use of knowing how deep the radiation, basically heat travels. And again, it may help us to figure out how thick the regular shield we have to make on our habitats in order to last. I could find some use in that. So that's there. Now, data bandwidth is the core weak point. That's why we had all the data is being collected. It's just that we are waiting for that data being dumped, so to say. So to do that, they have two puppies. One puppy is X-band system, which if you're not familiar, that simply means 8 gigahertz to 12 gigahertz bandwidth. Inside that is very high bandwidth, but it's very finicky and it does require you to point directly. And then you have a 3 of S-band. Now you're like, why the heck you have 3? Well, they are designed in such a way that even if it flips over or tops over, which again did happen with last rovers, last landers, they were like, they want to make sure that at least telemetry data can be done. So that is 2 gigahertz to 4 gigahertz, almost like your old school Wi-Fi. So that has more than enough coverage that no matter what happens, unless it's destroyed, they should be able to communicate. Penalty, it's only good enough for telemetry, and if they have to port data through it, it's gonna be painful, but it can be done. So X-band, the big pipe, and S-band is like, make sure telemetry is there, and they want to make sure all the software and firmware goes through S-band, and all the data payload goes through X-band. So this is the whole package. So what can we expect in the future? Well, this is a very good reminder for us all in our personal life. This literally happened because of 2024's failure. All the failure that happened in 2024. Okay, what if a valve goes booted? What if we forgot to check the LiDAR? What if a software did not did this job correctly? All of that, literally all of the learnings literally went into this, and that's why the landing was so boring. It's like, we figured it out, man. We did the testing, we figured it out. And why did NASA risk this kind of money? Because again, a lot of people are complaining. It's like, hey, we are having landing that falls over, we have this, that falls over, this, all of that, which again, NASA is bearing its teeth right now, but that's what's the whole point. The idea is, once this is done, once this growing pain has dealt with, they're gonna have cheap and easy access, and that's priceless. That's sure to take money. So that's why they're doing it. And what's the benefit of that? Well, expedited lunar R&D and on-site testing. It's one thing to say, oh, I have this lens system that can make sure that no lunar regolith actually sticks to it. How do you know? All the testing is fine and good. You can't test on continuous exposure on low gravity scenario. You have to go there. It's like, okay, just put it there. Cheap mission, take it and go. So flat out, it will expedite a lot of technologies that are in tier 4, tier 5, tier 6 kind of era to tier 8. So that is like a very easy, quick, rapid, boom, boom, boom. Like, and if the target is they're supposed to have at least 4 or 5 missions per year, and so they can rapidly improve. Basically, they will go from, oh, 2025 we had 2-3 missions. Oh, 2026 we have 5, 6, 7 missions, and the amount of technology demonstration would be like boom, boom, boom. But 2030 they're like, we got the moon, we good, we got this sorted. So that's the other. Now, biggest failure that's gonna be exposed now is the bottleneck of data links. Data is idiotically weak. Now, like, how did we do analog video data transmission in 1969? It's like without realizing that was barely 180p when we want 4K. It's like, yeah, the pipe is a bit fatter now, and you have to understand digital data does have this penalty where it's like, it's all or nothing. Analog data is far more forgiving. So we need to create a better system. Right now the systems are your surface asset, which has a limited solar surface area and a limited everything. It has to take a lot of its energy from its batteries and solar panels and dump it into radio screaming. So it screams from here to Earth. That's 1 light second away. Too much energy goes there. And be mindful, no matter, even if you have a laser beam, that will spread out a lot. If you have a radio beam, it's like duh. And you must have seen a good example of this in the movie Martian, where they're like, the dude is aiming something from Mars on a right point. How the heck it can work? Well, it does not work. It's just beam spreads out so much that it's aim in that area is more than good enough. So it does work. Penalty, bandwidth is lol. Bandwidth is just like lol. Like even 480p video cannot be reliably transmitted. So it's a way too stupid idea. So what are the next steps? Next step is lunar relay satellites. The idea is, instead of screaming 1 light second, just scream 1 nanosecond away. Not nanosecond, like at least few microseconds, so to say, and scream to the satellites. Satellite will take all the high bandwidth data without requiring you to dump so much energy into radio. It's going to absorb all the data because it will have giant solar panel. It's going to collect the data, buffer it, error correct everything, and then transmit directly back into Earth. And because it reboosted the signal, now the signal can be transmitted quite more effectively. Or you can even have a secondary relay on the lunar orbit, so Earth orbit, be it geostationary, be it because majority of degradation of signal happens when it's going through the atmosphere. So if you have a satellite that reboosted it, you could have a secondary satellite that absorb it. That way you can have much better coverage than deep space network. Again, that assumes you have a satellite that is doing the retransmission with boosted signal. Otherwise, we have to rely on deep space networks so we can have enough dish area so it can be collected. So that's the weak link right now in all the mission. We never reached this point, so we were not fixing it. Now we reached it. Now we are about to fix it. Lunar system. So few relay satellite in lunar orbit that should allow more than enough coverage where data transmission few milliseconds, microseconds away should dump all the data, like gigabytes of data, and that puppy can dump gigabytes of data into lunar Earth orbit, and Earth orbit to surface is like that's Starlink speed, more than fast enough. Now be mindful, it will have higher latency, so it's more for scientific payload rather than video calls. So that's there. But again, that's the whole point. So this whole suffering that they suffered in 2024, where it's like, oh, Calypso is a bad idea, lunar surface is not so easy. No, they know it's not that easy. That's why this high risk, high reward scenario, where it's like, okay, we're gonna risk 20 missions. They have that much funding, and then it's like at the end of like 5-6 missions, they're like, okay, now we are getting idea. End of 10 missions, like, okay, we good. End of 15 missions, like, we done, man, it's sorted. End of 20 mission, yeah, we have like 5-6 people we can phone up. It's like, bro, I need lunar surface. Like, I got you, fam. Put it, launch it, don't talk about it. So boring, like nobody should even talk about it. It's like, yeah, we do it. All the technological innovation that's gonna happen from 2025 to 2035 would be exponentially faster because of this cheap access. And be mindful, this is one launch in a system where there is another vehicle also going. So this is good. So this was my presentation on Firefly as a new lunar platform. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.